Hi, everybody. This is another recorded lecture to replace the one we had to miss because of the delayed start. So today I will be talking about the mathematical aspects of diffusion. So this is a part of chapter 5, the chapter in the book dealing with diffusion. Okay, so there's a lot to say about diffusion, and I will talk about it in more conceptual terms in the in-person lecture, but today I figured that for the recorded lecture, we can have some of the more detailed calculations. So the I think best model for diffusion, so the way to build understanding is probably the random walk. So the random walk is a process that is described by diffusion. It's really for these solid solutions, it's really quite a good framework because if we imagine a lattice, say, or a row of atoms, a bunch of lattice locations, say you have a bunch of atoms on in a row. So you have a row of atoms in a solid, and say you have a vacancy here. Then what can happen, the process of diffusion is simply the motion of atoms, the random motion, sort of thermally activated motion of atoms in the lattice. So what could happen is this atom right here on the left could hop over and take the place of this vacancy, leaving behind a vacancy in the spot where it was at before. So their new configuration would look like this. There would now be a spot opening up where that atom left. And of course, you could have hopping of the other atom over here. It's sort of equally likely. So if there's no bias in the direction, if there's no applied field, and it's just thermally activated motion, then we can represent that motion as just hopping um, from one location to an adjacent one. And if we think about it from the point of view of the vacancy, that's sort of easier. The vacancy, it's as if it can hop either to the left or to the right. So once you have any kind of vacancy, we can equivalently think of not the atoms moving, which is, what actually happens. The atoms hop over into a vacancy, but you can also just think of it as if it's the vacancy moving. And, the model for the random walk is just assigning a probability to these hops. So you say that um, every time step delta t, uh, a vacancy hops um, to an adjacent site. And we need to assign a distance to the sites. So the natural distance is, of course, the lattice spacing. So um, we'll assume that the hop size is equal to a lattice spacing. And it's easiest to consider the situation where, of course, there's no bias. So the probability of hopping to the left and right is equal. So we're going to assume that the probability of hopping to the left is equal to the probability of hopping to the right, which is 1/2. So if you think about what this is really like a series. You can think of it as a series of coin flips. You flip a coin. If it lands heads, you hop to the right. If it lands tails, you hop to the left, and you keep repeating. So our question is, what is the location X of the vacancy after n hops? So we take, suppose, big N number of hops and we ask, where does it land? Um, and let's assume initially we start at like a 0. We say we start at some origin of the coordinate system. So, okay. So what happens after n hops? After n hops, there'll be some number of them that were to the left, some number that were to the right, right? And so uh, the final location must be the number of steps that we hop um, to the right times A minus the number of steps that we hop to the left times A. You can think of it as sort of, this is our sort of X direction. We start at 0, and every time step we hop either to the left or right. So we either go to plus A or 2A or 3A here, or minus A, minus 2A, and so on. So we can imagine the vacancy sort of starting at the center of this coordinate system, and then we just hop back and forth. Could go this way, then this way, then we could go back, you know. And what you do is you count up the number of steps to the right, and in this case there's 2, and the number of steps to the left, in this case it's 3. So you see that in this example, the final location would be number of steps to the right, 2A minus 3A is minus A. So that kind of checks out. So this is our formula. Okay, so now we need some way of describing these final locations. This isn't going to be a deterministic process, it's random. So the thing that we need is the probability distribution. What we really want is the probability that we end up at this final location X. Turns out that's a bit harder to calculate. So the first thing we're going to do is calculate the probability of seeing a certain number of hops to the right. And this is the same as the probability of observing n sub r heads out of a total of n coin flips. So we have a constraint. So the total number of hops is, of course, if you add up the number of hops to the left and right, you get the total number, which means that the number of hops to the left is just the total number minus the number of hops to the right. So we never have to deal with the number of steps to the left. We can just replace it by the difference between the total and the number to the right. So this probability, it's equal to the probability of NR heads in N coin flips. Now, maybe you have seen this in a math class or something like that, how to calculate this probability. But the basic idea is that for any sequence of coin flips, like heads, tails, or right, left, right, we need to just count up the total number of sequences like that where we get NR heads. So if we have like a sequence of right, left, right, a sequence of flips, then we need to count the number of ways in which we have n sub r flips, right? So, and then we just multiply that number by the probability of any given sequence. So the probability of any given sequence is, of course, there's a 1/2 to the power of any given sequence that has that many head flips. So um, there's 1/2 to the power of n sub r. That's because, on each coin flip, you have a 50-50 chance of landing right or left. So the chance that you land right on any given flip is just 1/2. And so you multiply all those together. Then the rest of the flips, they have to be to the left. So the probability is that. Now you see it kind of, the n sub r parts cancel, and this just becomes, this is just equal to 1 over 2 to the n. And it's because all the sequences are equally likely, so this is really the probability of observing any particular sequence. Is any specific sequence. Okay, so then what do we multiply by? We need this number out in front that describes the total number of sequences that have n sub r flips. So the total number of, so if we have a particular sequence, the total number of rearrangements of the flips there, so if you flip the first flip, second flip, you can, if all the number of ways of rearranging those is going to be, uh, if you have a total of n, then there's n ways to place the sort of first flip, and then there's n minus 1 ways to place the second flip, and so on, all the way up to when you get to the last flip of the sequence, there will just be one way to place that one that's left over. But this is overcounting. This would be like the total number of arrangements of the flips, like all of the different orders of the flips, because we don't care about the order. We just care that the total number of flips to the right is equal to nr. So because, and this, by the way, this construction here where you take a number n and multiply it by n minus 1 and n minus 2, that's called a factorial. So it's n factorial. But this is overcounting. This is overcounting by all the number of ways we can rearrange the flips within all of the right and left flips. This would be as if this would be counting all the ways of rearranging the flips if they were all unique. So if they were all like numbered from 1 through 10. So, okay, just as an example, say n is equal to 3, then n factorial is equal to 3 times 2 is equal to 6. So this is the number of ways of rearranging 3 different flips. So say you have the first flip, the second flip, and the third flip. There's 6 different ways of arranging those if we don't, different orders of the first, second, and third. We could have landed the third first, then 2, then 1. We could have done 2, then 3, then 1. We could have done, what else is there? 3, 1, 2. We could have done 2, 1, 3, or 1, 3, 2. So those are all the 6 different permutations of the flips. But we know that of these 3 flips, say we have, say we're looking for all sequences with nr is equal to 2. We know 2 of them are going to be heads and 1 of them is going to be tails. Or the 2 is going to be to the right and one to the left. And that means we're overcounting because so if you have like 2 of them are heads, let's say these 2 are or to the right and like this 3-1 is to the left, then we're overcounting because if I write out these 6 possibilities, it's right, right, left, and then it's left, right, right, and then it's left, right, left. So those are all unique, but now you see you're going to start getting some repeats. In fact, I can highlight all the repeats. There's this one and this one, and this one and that one. So there's actually only three, or let's see, no, there's four. There's four unique sequences that correspond to having two steps to the right. Or sorry, I guess I messed up this one. This is no. Let me do that again. Okay. I'm gonna assign these two are right and this one's left. So let's do it again. So we have right, right, left, left, right, right. We have right, left, right, left, right, right. So that's these two are the same. And then we have right, right, left. So these two are the same. And then the last one is right, left, right. And these two are the same. So there's actually three combinations, three sequences, actual sequences that are unique. There's left, right, 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 left, and right, left, right. So the way you get that number three is you take the n factorial and you divide by the number of ways of rearranging amongst the n sub r steps to the right and the n minus n r sub r steps to the left. And if we do that, we would get, in this example, we would get 3 factorial over 2 factorial times 3 minus 2 factorial. So this is 3 times 2, which is 6, and then this is 2 times 1, which is 2. And then 1 factorial is just 1. So this is indeed 3. So basically this thing, this is called a binomial. And it counts the number of ways of having sequences with this many steps to the right. All of those different possibilities, no matter what order the steps to the right come in, because we don't care about the order, we just care about where the random walk ends up at the end. There's a special notation for this. Maybe you've seen it, maybe not. It's this binomial coefficient notation. It says that out of n total objects, it's the number of ways of choosing n sub r of them to be a certain type, like to the right. That's just the notation for this coefficient. So putting it all together, the probability of observing n sub r heads is going to be out of n total flips, you choose n sub r of them to be to the right. That's the number of ways of doing that. And then it's multiplied by the probability of observing any particular one of those sequences, and that's just 1 over 2 to the n. This is called a binomial distribution. So we can actually plot it. So let's plot it in some plotting software. I have some stuff for later, but let's do a plot. We'll do a list plot, and I guess we want a table where we're gonna go where m is gonna be our number of steps to the right, and we're gonna have a binomial coefficient. And let's say we're doing like 100 steps or something, or maybe 10, I guess. And out of those 10 steps, we're choosing m of them to be steps to the right. And then this is 1 over 2 to 10. That's just that probability. And m, the number of steps to the right, ranges from 0 all the way to 10, because we can either have 0 steps to the right and they're all to the left, or we have 10 steps to the right. I think this should work. Yeah, there you go. So it makes this kind of curve. The most probable value is 5, right? That makes sense because since you're equally likely to go to the left or right, then on average, the number of steps to the right should just be half of your total number of steps, right? So half of 10 is 5. You can see it's a nice symmetric curve. And what's cool is as you keep going out, you take more steps. This curve, and I should make sure that the software shows you all the points. The curve starts looking more and more smooth. And maybe this is familiar to you, but this is the shape of this is just the bell curve, the normal distribution. It's also called a Gaussian. You ever heard of like, I don't know, yeah, like standard deviations of like the normal distribution. This is used for like analyzing people's heights or things like that. So most things in nature are distributed according to this normal distribution. Um, Hopefully you've seen that, the bell curve, sometimes it's called. Um, and there's this theorem that actually tells you that all distributions that are derived from summing up a bunch of random processes like coin flips. So if what this is just, it's the probability of a sum of coin flips adding up to a certain value where, a step to the right is like a one and a step to the left is like a zero. It's the probability that you add up all those coin flips that you get a certain number to the right. And there's something called the central limit theorem that tells you that any such random process converges to a Gaussian distribution. Gaussian has a particular shape. I will show you the Gaussian shape on top of this. So um, there's a normalization factor. And this is the general form of it. It's 1 over the square root of 2 pi times the variance of the distribution. I'll tell you what the variance of the binomial is, but then it's an exponential of m, like the variable that we have here, the number of steps to the right, minus the average value. Now, the average value is kind of easy. It's just the total number of steps over 2. And then it's all of that squared. And then on the bottom, we multiply by 2 times the variance again. So, what is the variance of a binomial distribution? The variance, and this takes more time to calculate, so I won't do it. It's the total number of steps. It actually is proportional to the number of steps, which is interesting because, or the variance. So I'm going to do standard deviation, which is the square root of the variance. So you have a sigma squared is just the square of the variance. So the standard deviation, which you can think of as the width of this bell curve, grows like the square root of the total number of steps, which is interesting. And then it's multiplied by a quarter, which is just 1/2 times 1/2, because it's 1/2 of probability of stepping to the right and 1/2 is the probability of stepping to the left. And then let's plot that, from 0 to 100 and see what happens. And again, I have to force it to plot all the values. There we go. Perfect fit, right? It's like right on top of there. You can't even see the points anymore. Maybe I can make them large or something. No, okay. I think you have to do like this. Okay, there we go. So now you can see the points on top of the line. Maybe you can make them red or something also. Oh, no, I think this is Mathematica, by the way, so it's a little finicky with what you do. But there you go. You have red points on top of the blue line. Perfect fit. So that's the probability distribution, and it has this peculiar form. Well, not too peculiar, but it's, we don't want to deal with the binomial because that involves calculating factorials, which are very difficult to calculate. They lead to very giant numbers. So we're not going to do that. We're going to go with the central limit theorem and assume we have enough hops that our binomial can be well approximated by this Gaussian curve. And the Gaussian is super important. It's the fundamental solution to we'll see is the diffusion coefficient, so, the diffusion equation. So I'm sort of disappointed the book doesn't talk about that more. So, all right. So for large n, what do we find? We find that p n sub r is approximately equal to the Gaussian distribution. What is it? It's 1 over square root of 2 pi times the variance, which is n times a quarter. And then it's exponential of negative our x variable, the variable of interest is n sub r minus the average value, which is just n over 2 squared. And then on the bottom, we have twice the variance, which is 2 times n times a quarter. Now we're going to rewrite this in terms of the probability distribution for p of x. And where x now is going to be this guy right here, the final location of the random walk. So we just need to replace n sub r with, so if x is equal to n sub r, a minus n sub r. A, so this is equal to 2. So this n sub r combines with this one. This is 2 n sub r a minus n a. And now we solve for n sub r because that's what we have to plug in. And we get x plus n over a is equal to 2 n sub r a. And so n sub r is equal to 1 over 2a x plus n a, also known as x over 2a plus n over 2. This we have to plug in to n sub r, which is here. And then we're going to do one more thing afterwards. The number of steps that we take, we're going to assume we take a step every time interval, right? We kind of argued that there's, every time step delta t, we hop one time. So the number of steps, n, is just the total time that we move over the time step, the time over which it takes to make one of these vacancy hops. Okay, so let's figure out what that is then. It's p of x is equal to, all right, so what do we have here? It can sort of simplify a little bit. This is square root of pi times t over 2 delta t, right? Because we replace the n and one of the factors of 2 cancels. Then we have the exponential. This is kind of nice because the n over 2 cancels this one, n over 2, so we have a minus, and we're left with just x squared on top, and on the bottom there's a 4a squared from this denominator. The n over 2 cancels. And then we're left with 2n times a quarter, or n over 2. And n is just, so this is all times t over 2 delta t. All right, that's just n over 2. We can simplify some more. One thing we can do is multiply and divide this thing by the step. And it's worthwhile to do that because you'll see there will be some nice, or not delta x, but I guess I'm calling it a, the step size. Let's see. Yeah, a over a. Okay, so we'll see what that does in a moment, but it'll be nice because there'll be a certain combination of variables that comes out. So you have an a up top. If you put the other a inside the square root, you have uh, we're gonna factor out a factor of 4. We'll see why in a moment, but it's 4 pi times the coefficient here, and then the whole thing is times t. And then the coefficient is a squared, that's from the a. And then we factor out a factor of 4. So let's see, here we have, let's see, make sure we're doing this right. So we have factor of 4. So here we have, I guess, an 8, because the overall is over 2. So it's 8. Um, let me think a little bit. No, so let's not do that. Um, let's just, well, I think, trying to do a little too much at once. So let's just do pi times t, and then it's, so far we have a squared over 2 delta t. We have this kind of combination. And then up here we have exponential of minus x squared over 4t, and then it's a squared over 2 delta t. So we can see both in the exponential and in the square root, there's this combination of the time step squared over twice the time the hop size squared divided by 2 times the time step. And so that is called a diffusion coefficient. It's the hop size squared over 2 times the time at which it takes to make the hop. So this thing has units of length squared over time. It's very important. This diffusion coefficient kind of captures the idea that if you have a random motion, its distance, like on average, doesn't grow like linearly in time like it would if it was moving in a straight line with a fixed speed. Its distance in time just grows like the square root of time. So the length grows like the square root of the total number of hops that you take. That's what that captures. It's this idea that the standard deviation of your probability distribution for the final location, which tells you how far you went, that thing grows with the square root of time. So that's called the diffusion coefficient, which is tabulated for various things in the book. Okay, so let's rewrite this in terms of the diffusion coefficient. We have an a upstairs, and here we have a square root of pi t times d, diffusion coefficient, and then up here we have minus x squared over 4 times the diffusion coefficient times t. Now, there is a technical thing that happens here, so this is all good. It's just that this probability distribution is not quite normalized. What we really want is a probability distribution so that if we plot it as a function of x, like in units of some length, then we want to, if we plot this p of x, we want to make sure that the area under the probability curve, like the area under the bell curve, is always 1. This guy, because it was derived from the probability for the number of hops, Right? We actually derived this from the probability of having a certain number of hops to the right. This isn't going to be normalized in the right way. This one is normalized according to basically summing up over all the numbers of steps, like from zero and I can actually show you that. So in our little plot here, this binomial distribution, it is normalized. So if you sum m from 0 to 100, you get 1 because the probabilities all add up to 1, right? If you sum over all the different possibilities for having number of hops to the right, then they should all sum to 1. So we need something like that for the probability of observing a certain x. But because we now have things in terms of a length, it's the area under that curve is really an integration. So we actually need to multiply this by a normalization constant. I guess we're going to call it like some big constant C norm. It's just a constant that ensures that the area under the curve is 0. And in this particular case, the C norm is 1 over 2a. That's just what it is. There's a more rigorous way to find the normalization coefficient. You have to be very careful about actually going to the central limit theorem. So we just kind of skipped a little bit and just assumed that we can now treat the number of hops to the right as a continuous variable and just put it inside the Gaussian. And that's subtle. It's not, you have to be careful about the normalization when you do that. But in any case, we're just going to go with this because this isn't really a calc-based class. So you need a little more calculus detail to explain that. So we're just gonna say we need a normalization constant. That's what it is. And here is our final distribution. It's square root of 4 pi diffusion coefficient times time, and then it's exponential of minus x squared over 4 diffusion coefficient times time. This is the bell curve. It describes the position of a random walker with a certain diffusion coefficient. And now we can take a look at what these things look like. That's what's up here. It's 1 over 4 pi diffusion coefficient times time. So this is just that distribution. And I'm going to toggle the time here. At short times, it starts off with a sharp peak at 0. That's where the walker started. And as you evolve in time, the walker spreads out. Like the probability of finding it spreads out and it gets wider and wider and wider. Right? Because it's starting to hop around randomly more and more, and it can be found sort of in a wider range of locations. So that's what it looks like. And the higher you make the diffusion coefficient, the faster that happens. So if we increase it by a factor of 10, it zoops and spreads really fast. So the diffusion coefficient is like a measure of how fast the random walker is diffusing around. Okay, so that's the random walk. And this is the fundamental solution to the probability distribution of observing a random walk at a certain location. And if you have a whole bunch of vacancies in one dimension, say, then you can multiply the probability of finding the vacancy at any given location by just the total number of vacancies. And that gives you basically a concentration, a number concentration for the number concentration for vacancies in the material, assuming you start with like a whole bunch of vacancies at like the origin. So we're gonna kind of transition from using probability to concentration in a bit because that's more relevant for materials. But okay, so that's the random walk. The next thing to talk about is, I guess, the diffusion equation. So there are this thing, this function here, it solves something called the diffusion coefficient, the diffusion equation, which is called Fick's second law. This will be an important equation. Um, it solves this equation that the derivative of the probability with respect to time is equal to the diffusion coefficient times the second derivative of p with respect to x. This is a differential equation which describes the time evolution of the probability distribution. It describes this process of the random walkers spreading out. And it's called Fick's second law. And we'll talk about other solutions to this. This particular solution, the one that we derived here, assumes that you kind of have everything start at the origin. And then you ask, how does the concentration of random walkers or the probability distribution spread out over time? That's not usually the kind of initial condition we worry about in material science. Usually you have something like a fixed concentration on one side of a material. So so this describes time evolution, how things evolve in time. So usually Fick's second law, what it does is say you have some initial condition for your concentration or your probability distribution. By the way, we can replace these with just concentrations, and it would be the same equation. So usually in a material, you have like some fixed concentration, maybe in one portion of the material. Say you have some steady state value here, and then you assume that far away from the material, you have some other concentration like C0. And what this thing describes is like how does the interface between the two evolve. So if you start with like a very sharp transition between the two, how does this evolve in time? It smoothens out in time because since this ultimately describes random walkers moving around, if you start with a lot of random walkers on the left and not so many on the right, like a smaller concentration, it's more likely for the random walkers to move over from sort of the high region, the high concentration region to the low. They'll sort of just hop. And what will happen over time is that the concentration kind of smooths out. It will get smoother and smoother and eventually just sort of flatten out like that. That's what happens with increasing time. Very similarly to the Gaussian getting wider, but in a slightly different context where you have a smoothing out of an interface. Okay, so now let's talk about Fick's first law, which is also important. And in order to understand that, we need to talk about flux. So flux is a vector quantity. So it's a vector. And it describes the number of particles going through a certain area per unit time. So say you have like some area in space, some area, and you're observing particles moving through that area. So you have a bunch of particles and you watch them sort of go through this area, pierce the area. You watch them move through. The flux sort of describes the amount of particles going through. as a function of time. So the direction of the flux is perpendicular to the area. So you can always define a sort of perpendicular direction n hat to this area. And the flux is basically the number of particles going through that area per unit area per unit time. And it's in the direction of like the perpendicular direction to the area. So that's kind of what it is. In material science, usually you don't do the number of particles. So this would be like the number version. Just like we had the different alloy compositions, there's also a weight version. So there's like a mass version, in which case you don't count the number of particles, you actually count the amount of mass that passes through the area per unit area times time. So that's the other way of thinking about it. This one's sort of more relevant for materials. But the number one is more sort of, I think, fundamental because it, is actually describing the number of particles. Okay, so what do we learn about this? We actually can derive a law from it based on this idea of the random walk. So imagine we have a some direction x, and imagine this blue area is kind of going like this, piercing vertically, like that. And so we just want to count, if assuming everything performs a random walk, we just want to count the number of particles that are coming from the left and the right and that are going to pierce the surface. So let's say we have some concentration out here. Say here the concentration of particles is, we're going to put the location of this blue guy at just some fixed x, like some position x. And so then we know that the number of particles per unit time, say per unit time step of the random walk, there's going to be some concentration of particles out here. We're just going to say that this is x plus the hop step over 2. And then we're going to describe the particles over here as some other concentration here that's going to be. Okay, so let me just define the locations first. So this is x minus a over 2, and this is x plus a over 2. Okay, it's sort of better. And we're going to assume that the concentrations here inside these little blocks are uniform, which is going to be an okay approximation if our hop sizes are small and we sort of can just consider these uniform so that the concentration is not varying too much over this distance. So we know that the total length of this block here is A, and the total length of this block here is A. And the center is at x plus A over 2 for this one, and at x minus A over 2 for that one. And we're going to assume that the concentration in those blocks of particles is just C, x minus whatever it is at the center. So we're going to assume uniform concentrations. And here it's going to be Cx plus A over 2. So, okay, so what happens in one time step? Well, things are going to perform a random walk, right? In one time step, delta t. What happens? Well, we know that inside those uniform concentration regions, there's just particles like vacancies or atoms or whatever, and they're all just going to be hopping. This is in 3D, so we're going to assume that this is just X, and maybe this is the Y direction, and there's sort of Z direction coming out of the board. Um, so in 3D, the random walker, if we generalize the random walk process to 3D, we know that it no longer just hops to the left and to the right. It can also hop up and down, and it can also hop in and out, like along the Z direction. So it can hop in 6 different directions. And in one time step, the particles on the left, right here, let me do some other color. The particles on the left over here, only the ones that are hopping in this direction are going to be passing the barrier. Because if you take any particle in here and have it perform one hop by a distance A, then it's only the ones that are hopping to the right. Those are the ones that are going to sneak past this blue area, right? All the other ones that hop in the other directions, they will not move through the blue area. So, and because all of the 6 directions are equally likely, then we know that in terms of the concentration, like 1/6 of the concentration will move through the blue area. So the way to say that would be 1/6 of the concentration at x minus a over 2 moves through the blue line, the blue area. Okay, what about the ones on the right? Well, the ones on the right can also move through the blue area, but in the opposite direction. So the ones on the right, um, they are also particles that can hop in all the different directions, but now it's only the ones that are over here that move through the blue area, and it's also 1/6 of the concentration. Um, Moves through the blue area. Okay, so now we can derive what the flux is because through this blue area, right? We just count up the number of particles that move this way and subtract the number of particles that are moving the other way. And that gives us the total flux, the total net particles that move through the area from left to right in sort of the positive x direction. Now, these concentrations we're going to assume are, well, not assume, but what we mean by concentrations is going to be a number concentration. So it's a number of particles per unit volume. So we need a volume. The volume of these red blocks is going to be, it's the length of this blue area, like the length of the blue part, the area that we're considering. That's one dimension. Another dimension is, of course, the width of the block. That's just A. And then we're going to have to assign like a dimension for the box in the Z direction, which is just going to be some width. So there's this length A, and then we're going to assume this is just some width W. So the volume is L times A times W. Okay, so in this one time step, what is the flux? Let's just calculate the flux. The flux it's the number of particles going to the right. So that's 1/6 times the concentration of x plus x minus, I guess, a over 2. right? That's the amount of concentration. We need to multiply by the volume to get the number of particles. Actually, I think I'm going to run out of room, so I'm going to displace this and put this below. Okay, there we go. So, and then it's times LAW. So this is number of particles going to the right, or yeah, no, going to the right. The ones that are moving through the blue area. That's from the block on the left block. Then we have particles moving in the opposite direction from the right block. So it's minus 1/6 times C x plus A over 2. And it's again LAW. And then it's the fluxes per unit area. The area of the blue block thingy is what? It's well, we know the length of it is just this L, and then the width of it is this W that we assigned. That's just that blue area that we're looking sort of looking at the edge of it right here. It's got a here, I should show you the blue area is just this guy. Okay, so the area is just L times W. And all of this happens in time delta t. So we have some cancellations that happen. You have the LW canceling the LW, canceling the LW. And now, um, and we know the flux is in the x hat direction. That's the normal to the surface. It's sort of this way, x hat, the perpendicular direction to the surface. So, okay, what is this J? There's a factor of 1/6 delta t that comes out. And then there's a factor of A also. So I guess there's an A up here. And here we get an interesting kind of difference between concentrations. It's x minus A over 2 minus x plus A over 2. Now, unfortunately, we can't move on without doing some calculus because we need to approximate these concentrations somehow. And if the concentration is smoothly varying, which we've sort of been assuming the whole time, then we can approximate these concentrations by using the Taylor series, by approximating a function by its behavior at a certain point and then using derivatives and stuff. So I don't know if you haven't seen any calculus, this might be totally meaningless to you, but if you have like a function as a function of x and it's some smoothly varying thing, if you want to know what its behavior is at a certain point, it's described by the value of the function at that point. And then you can look at the variation of this function around that point by considering the sort of local slope. The local slope is just the derivative of the function dc dx around that point. And you can keep taking higher order approximations near that point. So you can first approximate it as a line, and then you can add a correction that sort of takes into account how curvy the line is, how much deviation there is from the line near that point. That would be the second derivative. It sort of describes the curviness of the line near that location. And there's a general kind of approximation that you do, which is called the Taylor series. And it just says that the concentration at a certain location y close to x is approximately equal to the concentration at x plus the derivative of the function with respect to x evaluated at x, basically, times x minus or times y minus x. There we go. And then um, plus 1/2 times the second derivative of c with respect to x. So two derivatives. I know if you don't know derivatives, this is sort of meaningless, but this is basically like the slope of the line near the point x, and this is like the curvature. Um, Near that point x. And there's a factor of 2 that's there for technical reasons. And this is x minus y squared. And, or if you want to sort of make more symmetric, is say y minus x. Okay, so when x is equal to y, the correction terms, and there's higher order stuff, but we won't care about that. So when y is equal to x, of course, you just get c of y is equal to c of x, which makes sense. And otherwise, you have to add these terms. So as you move away from x, as y moves away from x, you'll like pick up the sort of linear portion of the line, and then the curvature and so on. So let's see what happens here. Let's use this Taylor series to approximate. So J is approximately A over 6 delta T. So what is this first one? So Y is equal to X minus A over 2 in this case. See what we get. So we get C of X and plus dc dx. That's the derivative evaluated at x. Y is now x minus a over 2 minus x. So the x's cancel. And then we will need that second term, 1/2 dc dx squared. Or maybe we won't. Actually, I don't think we will. So we'll see what happens. I guess we won't, but it's x minus x plus a over 2 squared, and so on. So that's for that first term. This one. That's all this stuff. Now we subtract the second one. We subtract this one. For this one, y is equal to x plus a over 2. We need to approximate the function on the other side of x. So we again have c of x plus dc dx, and this is now x plus a over 2 minus x. So those cancel. And then just in case, we can add that second one. X minus a over 2 squared, and so on. All right, so let's see what cancels overall in here. And then, of course, this is all along x hat. So let's see what cancels overall. This c cancels this c. Okay, so actually, since these x's cancel here and here, there's a plus sign here, but there's a minus sign here. So actually, this cancels that. So the second order term is not contributing. So the first non-zero thing that we get in this approximation is this guy. Because you see you have a minus sign there, but you have a plus sign there. So what this is, right, is, let me do black color again. This is A over 6, 6 delta T. And over here we have dc dx minus a over 2. And then we subtract dc dx times a over 2. So they add together, actually. These two combine. This is in the x hat direction. And what you get is there's a factor of a that comes out. It's a squared over 6 delta t. And we pick up a minus sign. right? There's a minus sign here and a minus sign there. And it's dc dx along the x hat direction. So it tells you that the flux due to diffusion, due to random walking, is going opposite the slope of the concentration curve, which makes sense because random walks tend to move from regions of high concentration to low concentration. So it moves down the slope of the concentration curve, moves from high to low. And this is written another way. I guess you can remove the vector and just say if it's a one-dimensional current, one-dimensional flux, this is just minus a squared over 6 delta t dc dx. And now we identify in here an interesting quantity. Look at this thing. This is the step size squared over 6 times delta t. That's actually a 3D diffusion coefficient. The general form for a diffusion coefficient is the step size squared over twice the dimension that you're working with times the time step. In this case, for 3D, it's a squared over 2 times 3, which is 6 delta t. So that's the diffusion, 3D diffusion coefficient. If you recall when we did the 1D stuff, and the 3D came in because we, talked about hopping in 6 different directions. When we were doing the coin flip, we only had 2 different directions. So we ended up having that the diffusion coefficient, where is it now? Yeah, see here, this is the 1D one, 1D. It's the step size squared over 2 times delta t. In 3D, there's more directions to move, so the diffusion coefficient is different. It's divided by 6. It's kind of like saying, so in 1D, if you just move along one direction, you get a lot further because your only options are moving along that one direction. If you're in 3D, you have 6 possibilities in which to move every time step, so you don't get as far because it's much easier to circle back to where you started. So it's as if your diffusion is sort of decreased by a factor of the dimension. So like moving in 3D is like a third as good, I guess, in order to sort of get away from where you started. That's like a very rough, intuitive thing. But here it is. If we identify that with the 3D diffusion coefficient, that means our flux is, along one direction anyway, is minus the diffusion coefficient times dc dx. There's a way to generalize this. If we think about any kind of area in 3D, the generalization to 3D is that, J becomes a proper vector. And then what this tells you is that the random walkers, the flux of those random walkers always moves down the concentration slope. And the 3D version of slope is something called the gradient. It's just something that points along the direction of steepest ascent, like the direction which you're ascending the concentration the fastest. And so in that case, the Fick's first law, as it's called, is just the gradient of the concentration. So that's like sort of the 3D version. This is it is still the 3D version because we're using a 3D diffusion coefficient, but it's along one direction if you're just considering the flux along one dimension. Okay. So this is called Fick's first law. And those are the 2 major laws for diffusion. Fick's first law, it tells you about how the flux of particles move when they are performing a diffusion, a random walk. And the second law tells you about how the concentration evolves in time. So in some sense, Fick's second law tells you about what happens as a function of time, whereas this first law is most often used to describe the steady state flow of particles. If you have some concentration differences set up that are like permanent and you're just observing particles sort of diffusing from one place to another, and things are no longer time dependent, you just have constant fluxes, then you would use fixed first law to figure that out. So I'll do the examples for usage of these laws in class, but I was hoping to give you sort of detailed derivation of both that maybe is outside the scope of the book, but hopefully it's useful to see sort of where it comes from. And I think it's very useful to derive all these things by thinking about particles hopping on a lattice, whether it's 1D along the lines where you can connect it to coin flips, or, in 3D where we're thinking about particles hopping along the X, Y, and Z directions. It's very fruitful because you can get a lot of good intuition about what happens and why these formulas are true. It does take some math to get there, but they are just simple consequences of this kind of random motion. They're not like I don't know. They do have a complicated mathematical form, but the underlying process is actually a pretty simple one. All right, so I think I'll leave it with that for now. I'll say more in class.